Hey, welcome back. This is now 1.3, and we're looking at differential equations as models. And we'll begin with the simplest differential equation, which is probably the most unrealistic differential equation, but serves as a great beginning as an introduction to the topic. So the first one, population dynamics. And we have the rate of change of a population with respect to time is proportional to the population at some given time. And here we'll presume that this k value is greater than 0. Okay, so let me write again what this means. It's the rate of change of the population is proportional to the population. The great thing about a lot of these models is that how intuitive they really are, because you can imagine just coming up with this on your own. Maybe you're in a biology lab or something and you're dealing with fruit flies. So let's label this as an example. Right? And maybe this is like a petri dish you're looking at, and maybe you have 3 fruit flies and you're considering the rate of change of fruit flies in that dish as a result of their interaction. Okay, so which rate of change would you think would be bigger? The rate of change of the population in this petri dish, or the rate of change of population in this petri dish? Let's call this dp1 versus dp2. Well, clearly the second, dish, your rate of change of the population is going to be greater because there's more fruit flies there. If you only have 3 fruit flies, there's not going to be a lot of reproductive activity, right? So you wouldn't expect the rate of change to be all that great. Okay, so it's an intuitive idea, and a lot of times you could take these intuitive ideas and translate them into differential equations. Okay, then you could add in more and more factors and make them more and more complicated. Just the problem might be that solving those resulting differential equations may be very difficult. Okay. So let's look at one of the problems from WebAssign where they try to make the model a bit more interesting. Okay. So let me get the question out so I don't have to reproduce it. Okay. Yeah. So assume, so they're adding immigration into the population model. So they're presuming that they're not dealing with just one petri dish where there's just like 3 maximum flies and you can't add any flies in there. It's not like that. They're saying they want for it to be the case where you're adding more flies into the mix. So the first question, assume the absence of immigration and immigration. Assume that in the absence of the immigration, we have the generic population growth differential equation. And then determine the differential equation that would happen if you allowed immigration. So one way to model that would be just to add in some sort of factor. So in this case, they want the factor to be R. So to model immigration, just use the regular model and then add in R that would represent the people that are being, or the flies in my case, being thrown into the question. Okay, so very interesting. You can make your own models, obviously at home if you want to, and then eventually you'll be able to solve them and make predictions about the way things behave. One thing that maybe is a little confusing is that you can use the same models for different phenomena. For example, radioactive decay will use basically the same model that the population dynamics model used. So here, radioactive decay will say the amount of radioactive substance present at time t is proportional to, or the rate of change in the amount of radioactive substance is proportional to the amount of radioactive substance. Okay, so the same formula from above, just different letters. And of course, in this case, the K value is going to be negative. The rate is going down. You can think of it. So, yeah, just don't let that confuse you. Let's look at another model, Newton's law of cooling. And we'll be returning to these models here later on. We're just kind of introducing you to them right now. So Newton's law of cooling, basically the rate of change of the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So if you worked at Domino's Pizza, you could use this model in order to figure out how long you could let a pizza be sitting in your lobby before you have to kind of throw it out, before its temperature decreases. Also, if you work in a foundry, you need to know how long it takes for some of these things to cool off. So you have a mold and you're pouring, liquid metal into it, and you want to know how long you have to wait until you can take the mold off of it. You could use this to figure that out. So let me just write it out again. It's the rate of change of temperature of an object is proportional to the difference between the object and its surrounding temperature. Okay, and if you look at this differential equation, it's actually not much more different than the radioactive decay and the population growth equations. Just it seems you have an extra term, and when you solve these, you will see that they kind of have the same solution, kind of. Let's look at spread of disease models. So these models will say the rate of change of people that are infected is proportional to the product between the number of people infected and the number of people not infected. Okay, so let's see, X is number of people infected, and Y of T is going to be the number of people not infected. Okay, let's go ahead and look at the story problem here. So unfortunately, I already have the answer sitting there, but suppose a student carrying the flu returns to an isolated college campus of 9,000. So at time 0, the number of people who are not infected, I guess 8,999, but yeah. Yeah. That's not gonna work. I'll just say there's 9,000 people there on campus. Determine a differential equation governing the number of students X of T that have contracted the flu. So X of T is basically the number infected. And they're saying basically what I just said, the rate of change of the number of people with the flu is proportional, or the disease spread, the rate at which the disease spreads is proportional to the number of interactions between students with the flu and students who haven't yet contracted it. Use K for the constant proportionality. So it's basically the same formula, except you're able, because you have that 9,000 up there, you're able to say that Y of T is basically 9,000 minus X of T. So you can eliminate the Y variable altogether. And then rewrite your spread of disease equation not as kxy, but rather as k times x times 9,000 minus x. Okay, so that's spread of disease stuff. Next one is mixture problems. Okay, so 5, I guess we're on mixture. And what's happening here is you have some potentially salt water mixture, and they're calling salt water brine in the book. So brine solution coming out of this pipe and being dumped into a big tank, which is being mixed. Okay. And there could potentially already be stuff in the tank, and then on the tank there's a little tube coming out of that, where the stuff in the mix in the tank is being dumped out. Okay. Your goal is to kind of figure out the rate of change of salt in the tank. Okay. So going into the tank, there's going to be a rate of the salt water going in there. So they'll usually call that something like R1, and the units will be in gallons per minute. And then within that solution, they'll probably tell you how many pounds of salt are mixed in. So they'll give you some other value, Q1, which will be in pounds per gallon. Okay. Then on the way out, there's going to be a rate. So R2 may be gallons per minute. But the amount of salt in the mix that's going out is dependent on the fluid in the tank, right? So the amount of salt in the tank, they're going to say is A of t, and it's variable, right? And then they'll probably tell you how much fluid is actually in the tank at time 0. And I'll just call that V sub 0. They probably use different variables in the book. Okay. And then the key to understanding this problem is that the rate of change of salt in the tank is equal to the difference between the rate of salt going in and the rate of salt going out. Okay, where both of these will be in the units of pounds per minute. And a lot of times I just kind of hang my hat on figuring out the right units, and that kind of, I can kind of back engineer those two values, but let's look at them a little more closely, shall we? So the rate of salt going in is going to be the product between Q1 and R1. Okay? And you can see if you took the product of Q1 pounds per gallon and R1 gallons per minute, you end up with the appropriate units. The rate of salt in is Q1 R1 pounds per minute. Okay. So usually that's pretty easy. The harder part is the rate of salt out, because the amount of liquid in the tank could be variable. And so the rate of salt out, then the hard part is figuring out that this Q part here. That becomes difficult. And all it is just the amount of salt that's in the tank, which is A of t, divided by the amount of gallons that are in the tank. And the amount of gallons in a tank is kind of a linear thing. It's dependent on the difference between the rate in and the rate out. So you'll have, you can find the difference between R1 and R2, and that tells you kind of the slope, if you will, or the rate of change of liquid in the tank times some time unit, plus where you start, which is the amount of fluid initially in the tank. Okay, and those units will then be in pounds per gallon, and you just simply multiply that by the R2 value, which is in gallons per minute, and of course then you get your pounds per minute that you're after. Okay. It'll become more complicated as we go through and see some later kind of problems where they have multiple tanks to deal with. The initial problems given in the exercises are fairly simple because the rate in and the rate out are equivalent. Okay, so in problem 3, it says suppose you have a large mixing tank that initially holds 500 gallons of water. So let me just draw my little picture again. Okay, so here's my tank. There's junk coming out, there's junk going in. So again, the tank initially holds 500 gallons. There's 80 pounds of salt that are initially in the tank. I don't think that's going to be necessary for us to know. Pure water is being pumped in, so this Q1, which would have been the pounds of salt per gallon in that mixture, is actually 0. So pure water means there's no salt in it. So 0 Q1, or rather we just put 0 pounds per gallon. So Q1 is just 0. And then the rate at which it's going in is 5 gallons per minute. And then the rate at which it's going out, it's the same. It says it's going out at the same rate. And then it's pretty simple. You can just plug everything into that formula here, the rate of salt in minus the rate of salt out. So your dA with respect to dt is going to be, well, let's do it one piece at a time, right? So let's do the rate of salt in. Rate of salt in is just going to be 0 times 5, right, which will be 0 pounds per minute. And then the rate out is going to be our A of t divided by, here the rate R1 and R2 are the same, so R1 minus R2 will be 0, and then plus the initial amount. In other words, the amount, because the rate in and the rate out are the same, the amount of liquid in the tank is not changing. It's not going up, it's not going down. And then times the rate at which it's going out, so the R2 value basically, and we're going to get A of t all over 100 pounds per minute. So finally then the differential equation dA with respect to dt will just be A over 100, or well, 0 minus A over 100. It has to be rate in minus rate out, sorry. So 0 minus A over 100, which of course could be negative A over 100. Make sure you're using capital letter A in your answer, and it's always annoying when you actually put the wrong, to put a capital A, you get it wrong. Anyways, let's go on to the next problem, draining tanks. Section 6, draining a tank. Okay. So what we're talking about here is some sort of bucket or some sort of thing full of water. The area of the top is A sub W, or yeah, A sub W. And then there's going to be a little hole in the bottom of this bucket, kind of down here. And maybe some sort of pipe on that hole, and the water is going down out the pipe. The area of the hole is A sub H. Okay. And then we're going to use a bit of physics to figure out the rate of change of volume, and from there get the rate of change of the height of liquid in the tank. Okay, so got to use, like I said, a little bit of physics. First off, the speed of water leaving the tank. We use like a potential energy, those physics formulas that I don't remember all that well, but if you use those, and they tell you how to put it all together in the book, you'll end up with the velocity of the water leaving the tank being the square root of 2gh, where g is the our gravitational constant, right? Let's see what else. From there, we can talk about the volume of water leaving the tank. Okay, so we can just multiply the area of the hole times this velocity, and you'll get a sub h times the square root of 2gh. And then the rate of change of the volume will just be the negative of that. Okay. And also we can note so also the volume of stuff in the tank is equal to just, the area of the top of the tank times the height of liquid in the tank. So you can take the derivative of this, both v and h are dependent on t, and you have another differential equation, dv with respect to t is equal to aw times the derivative of h with respect to t. And then you can combine the formula, these formulas from step 2 and step 3 here in my little outline, and produce this following factoid. So hence from 2 and 3, we get AW times the rate of change of the height with respect to time equaling negative AH times the square root of 2GH. And then solving, we can get a formula for the rate of change of the height of water in the tank, which is kind of what we want for our homework. Okay, so this will be negative A sub H all over A sub W times the square root of 2GH. And don't forget, H is variable. Okay, I think when I went in here and I did the problem, I got that wrong, because I should have used a letter H for my answer. Okay. One other thing to worry about, and like question 4 here, when you go to do your homework, they're going to give you, like, the radius is 5 inches, the gravitational constant is 32 feet per second squared, the height of this cube thing, and the volume will be 100 because it's a cube, but note everything's in feet. Okay, so when you're working with this radius, be very careful. You want that in terms of feet. So you're going to have to turn that into 5/12 feet in order to use it in your formula. Okay, so that's why I got it wrong when I did it. Okay, so I'll leave that problem to you. You can do that. I think you could do that. Let's look at, let me just introduce series circuits. So we have Kirchhoff's law that says the amount of impressed voltage is equal to the sum of the voltage of the drops in the loop. Your inductance, second derivative, plus the resistor stuff, plus capacitor stuff. And the problem in here, that they may not necessarily have all 3 inductance, resistor, and capacitor. Like in this loop, they don't have the capacitor, so you just leave that part out of it. It's the impressed voltage is equal to the sum of all the little things that are being thrown in your loop. Okay, so in my problem in number 5, I didn't even necessarily have that. It would have just been E equals. So all we have is L Q over dt plus R dq over dt. And what is the I part? Well, that's just from your charge, right? So you go back in here, they'll give you a relationship that will allow you to get I. So I, the current is equal to the derivative of the charge. Okay, so I is derivative of the charge. So we can rewrite this as E equals L, first derivative, second, so this would be di over dt plus ri. And then in the question, they want you to solve for di over dt. Okay. The next one is falling bodies. Is this 8? Jeez. All right. Falling bodies. And basically, you're using Newton's second law. Force equals mass times acceleration. In particular, we'll think of acceleration as the second derivative of the position function, and you probably saw that back in Calc 1 or Calc 2. So we can write this as this force formula as differential equation, mass times acceleration equals mass, and the acceleration is just going to be the force of gravity, and you assume that the negative direction is downward. Okay, so you can divide by m and get this formula. Okay. You can make this a little bit more complicated, and that's what they're doing in problem 6 by adding in air resistance. So you can augment the model by adding in air resistance. And again, this is one of those intuitive things. It will say air resistance is proportional to the velocity of the object. So the faster you go, the more wind you're going to feel in your face. Or if you're like this Einstein guy, the more wind he's going to have in his hair, apparently. So anyways, we can rewrite our model now. Mass times acceleration equals mg minus k times v, where this is the air resistance. And then if you want to, you can write it all in terms of s by replacing the velocity with the first derivative of the position function. Okay. In particular, I think that's kind of what, okay, so they're putting everything in terms of v in their problem. So you could also rewrite it as the derivative of v with respect to t, first derivative, equals m times g minus k times v. And if you solve for dv over dt, you just get g minus k, apparently it's v squared. Oh, for their problem, the resistance is proportional to the square of the instantaneous velocity. My problem, and when they first introduce it in the book, they just say the air resistance is proportional to the velocity. So that answer is a little different. Okay. Okay. Yeah, pretty sure that's what they're doing. Yeah, there's just proportional to the velocity. Okay, I think maybe that will do it. Acceleration, the upward direction is positive. Okay. There's one other question. I think I want to hit this one because for some reason I don't want you spinning your wheels on it. I don't want you having to guess your way through it, but Newton's universal law of gravitation for the free fall acceleration a of a body such as a satellite shown in the figure falling a great distance to the surface is not the constant g. Clearly, further away you get, it's going to be variable. Okay, so rather than have the acceleration just equal to g, we're going to say the acceleration is inversely proportional to the square of the distance from the center of the Earth. So they give you this formula for a, which is k all over r squared. Okay. And the first question, in the first box, they want use the fact that the surface of the Earth, r equals big R and a equals little g to determine k. So a is g, little r on the surface of Earth is big R. So we can solve for k, that'll equal g r squared. So just don't overthink this. I'm an overthinker. The second question then, if the positive direction is upward, so we need a negative there, use Newton's second law and his universal gravitation, law of universal gravitation to find the differential equation for the distance r, and they want the second derivative. So you think of the d2r with respect to dt, it's kind of like the second derivative of the position function, and of course it's just going to be equal to the negative of the acceleration, which we were given to be k all over r squared, and negative. And then you can replace k with what we just found in the part 1 of the problem. So it would be negative g big R squared all over little r squared. Okay? Just so you don't get into the problem and start overthinking the heck out of it. So anyways, there's that. Hopefully that helps. I'm not by any means a physicist type person. I'm more of a theoretical math person. So hopefully that'll, I mean, I took physics and everything, but hopefully that'll get you through the problems. Okay, so thank you for watching as usual, and we shall see you next time. Okay.